Your support helps us bring you programs you love. Go to wyomingpbs.org, click on Support, and become a sustaining member or an annual member. It's easy and secure. Thank you.
This is what Wyoming looks like today. Towns, roads, and ranches. Cows can be seen everywhere. Wolves and bison are making a comeback. If we go back 500 years, we see villages, pathways, and migration corridors. Humans have an impact on the landscape, but not to the degree of modern times. Wildlife are plentiful. There are huge herds of bison, bighorn sheep, and elk. Wolves roam vast areas of territory, and horses have not yet been reintroduced to the Americas. But what if we go back 13,000 years and before? What did Wyoming look like then, and why has it changed? At the northernmost edge of Wyoming, in the Bighorn Mountains, lies a cave that has been collecting information on that very subject for over 40,000 years.
Production funding for Main Street, Wyoming is provided in part by the Wheeler Family Foundation of Casper and by the members of Wyoming PBS. Thank you.
First time I was in Natural Trap was 1967. We would drive up to the cave and rig off the axle of our vehicle and drop the rope in, and we'd rappel in and climb back out and rappel down and climb back out. At the bottom of the cave was actually a mound, and that mound was really soft and crumbly and had bones and stuff in it, but it was all modern, rabbits and deer and things like that had fallen in.
Natural Trap Cave is located in northern Wyoming. It's at the base of the Bighorn Mountains, right near the Bighorn Reservoir. Natural Trap Cave is a karst cave. It's made out of limestone. Water percolates in through the limestone, and then it dissolves away the interior, leaving just a shell. And then when the opening falls in, it's very similar to how a sinkhole forms, but instead of forming a sinkhole, it forms this cave.
It's called Natural Trap because things fall in. And the reason why the grade is there is because, we didn't want people and cars going in there. At least the BLM did not want people and cars going in there.
Starting in 1970, Dr. Lawrence Lohendorf helped to recognize the scientific significance of Natural Trap Cave by conducting an exploratory excavation of the cave, as well as taking steps to preserve the integrity of the specimens there for future research. By the mid-1970s, a team of paleontologists led by Larry Martin from the University of Kansas and Miles Gilbert from the University of Missouri began the first major excavations of the site. What they found was one of the most complete fossil records spanning from the Pleistocene into the Holocene.
The Pleistocene epoch is also known as the Ice Age because of the cold fluctuations that occurred during that time. Pleistocene epoch lasted from about 1.2 million years ago to about 11,500 years ago. Many of the megafaunal or large mammal species that existed during that time went extinct, such as saber-toothed cats, dire wolves, short-faced bears, camels, mammoths and mastodons. All of those things went extinct right around that time. And that's the border between what we call the Pleistocene and the Holocene. So the end-Pleistocene extinction event is a conundrum that many scientists have been thinking about for a long time.
The primary ideas are human influence. When humans came to North America, they wiped out all the megafauna, the large mammals, for eating. The other hypothesis is that climate change did it. And that makes sense because that's when the glaciers were also going away. And large mammals tend to be particularly sensitive to climate change.
Our project doesn't really take into account human arrival, but we are looking at how climate affected the animals, both in their genetic material and in their morphology. And we're correlating that with the pollen data that we're collecting so we can recreate the flora at Natural Trap Cave at that time. So we try to get an entire recreation of the end-Pleistocene habitat in northern Wyoming.
Natural Trap Cave is a challenging place to work. I say I have a very strenuous commute every day to get to my field site.
It's such a complicated project because of how you have to get into the site. Since there's no other way to get in, you have to rappel in on a single rope, and then you have to ascend out using hand ascenders and your own steam.
We put out an announcement to the caver societies and the grottos, the local grottos, and we had people show up in droves, and they have been the most incredible, helpful people. They really take initiative and have been incredibly integral to the process. Juan in particular, who's our head of safety, he's been volunteering for weeks at a time every summer in order to make this project happen, and we absolutely couldn't have done it without him and without other members of the Wyoming community.
The uniqueness of this cave is twofold. One is that it's a pit cave that is on top of a ridge. So it funnels traffic, animal traffic, down this ridge. And then also unique to this particular pit cave is that just before you come to the 15-foot hole in the ground, there's a little drop off. So you don't see it until you're right on top of it. And then it's almost too late, and it has been for many animals. This particular cave has an 82-foot entrance drop. It's about a 15-foot diameter hole, and it bells out in all directions from that hole. We go down a ladder onto this ledge. We have safety lines, and then there's a grid over the top of the cave to keep people and animals from falling in now. And we do all our rope rigging off of that, but to access this cave, you have to rappel in and ascend out. I can't train people to be super proficient vertical cavers. There's no way in the short amount of time we have. I get them to a level that I feel comfortable I can effect a rescue.
Natural Trap Cave is a really important fossil site, not only because of the quantity of fossils that are coming out, but also because of the preservation of the fossils. The cave is always cold. It never gets above about 42 degrees Fahrenheit. It's also very wet, probably about 80 to 90% humidity, making it a little bit like your refrigerator at home. This site can really inform us of not only changes in genetic variability in the animals, but also of the environment in northern Wyoming during the last ice age.
The team has set up 3 active excavation sites within the cave. They are known as the Bison Saddle, the Cheetah Pit, and the Catacombs, based on some of the early specimens out of each of them. The excavation work is primarily conducted by volunteers under the supervision of lead scientists in their respective fields. The volunteers are members of the caving community, students in related fields, and others just interested in the scientific significance of the cave. For Dr. Julie Meechan, her field of expertise is megafauna. She is interested in the functional morphology of the large mammal remains in the cave.
Okay, was it a humerus? Yeah. Functional morphology is the study of body form and function. So for example, a running animal like a cheetah would have a much shorter upper arm or humerus than it would lower arm bones or radius, whereas something that climbed for a living would have a much longer upper arm bone than lower arm bone. So in terms of fossil material, we're looking for diagnostic pieces. We need to be able to identify the species that it came from and the body part that it came from.
It's in 3 pieces.
Oh, it's in 3 pieces. Wow.
But they're well-fitting pieces.
They are. This is another proximal metapodial of a cat. When we have a lot of people down here, as a team leader, my job is basically to run around and manage everybody, help the volunteers, identify specimens. So I don't get to do a whole lot of excavating myself. Nice, that's definitely a carnivore. Looks like a wolf, yeah, yep. Nicely done.
That was
I've been joking that I've just been playing stone versus bone this whole time, trying to tell what's a rock versus what's a bone. So when you find something that, for sure is bone and you can start to identify it, it's pretty exciting. As a volunteer, I feel like for me it's been an even bigger learning experience than for a lot of the scientists and professors and everyone who have years of experience with this. There's bone right along here, here. That's all sections of bone, and we pulled a piece that broke right out of here. So we believe that, hopefully this is all from the same horse. So that, maybe even could be a tooth. We'll see once I dig up the ends. But the side looks similar and has some of those same divots.
When you're digging for fossils, most of the time you don't find anything. You're just digging through all the dirt, and all you're finding is more dirt and rocks. But when you see a piece of bone sticking out of the ground, and you dig around a little more and a little more, and you figure out that it's something big that's buried there, that's extremely exciting. If you think of digging up dinosaur bones that have been sitting out in the desert for 100 million years, they've pretty much turned to rock. These bones have only been down here for maybe 10,000 years, 15,000 years, 20,000 years, something like that. So they're actually still bone. They haven't mineralized yet. This area, since we're right under the hull of the cave, this is where water's going to come through. So these sediments are fairly waterlogged, which means that the bones they're not going to really dry out. So they're just, which keeps them pretty fragile. It's a vertebra of something. I'm not sure what yet. The problem is that it's in mud, which is making it very fragile, and it's also surrounded by gravel. So I have to dig around the rocks to get the rocks out, and then dig around the fossil to get the fossil out. So it's taking a very long time. So you can even see how it's starting to come apart a little bit right there. So see how it's broken right there? So what I'm trying to do is not break that more, so I have to be very careful when I'm taking the rocks out.
So there's that full tooth there. As the dirt starts to crumble off. I feel lucky that this is my first paleontology experience. Finding a lot of things. A lot of field sites are not as productive as this. I mean, even within this field site, a lot of the areas aren't as productive as this wall.
Okay, how about A12?
201.
What's A1?
A1 is 202.
This instrument, it measures distance and then a horizontal angle and vertical angle. And so it takes those 3 bits of information, and the computer can extract that and turn it into X, Y, Z coordinates. And so that way we end up with a grid, and then we can bring it into CAD, and then you can look at it and say, okay, this bone was sitting this way, this one was sitting this way, and then you can map it like that. It's probably going to be our last chance to be in here for a while, and just want to make sure everything's right. This is pretty high up in cool things I've done. It's exciting to be a part of the project.
When we find a bone, we do take measurements of the elevation that it was found at, the position it was found in, which section of the grid it was found in. For this one specifically, since we're digging up all these teeth right in the same area, we have a range where they're found, so you know that they were found together.
The mouse ran right around my foot and then ran back. I was like, okay, don't run up my pants. That's all I ask. So there's a giant grate over the cave because in 1971, someone almost drove their VW Beetle into the cave. So big things don't fall in any longer, but small things get trapped all the time. Some of the things that we have found over the years include several pack rats, The first one, we actually named him Packy Le Pew, and we did a taphonomy experiment on him. Taphonomy is a study of the breakdown of tissues and the process of fossilization. This is actually Packy right here. Packy is very hard and desiccated. He's very dried out. He's been here the whole time, and he's basically just a packet of bones with some skin on it and fur.
Pack rats are super cool. They make these giant nests, and there's pack rat nests along the rim of the cave. They go out and they collect every bone and every cool piece of wood that they find within a 5-kilometer diameter. You can imagine these wood rats precariously kind of perching on the rim of the cave, and then they're scurrying around and they kick all their prized treasures down into the cave. And so you get this rain of fossils coming down into the cave. It creates this really nice, dense concentration of bones that gives a really clear picture of the community. We've radiocarbon dated a lot of bones. We're getting age ranges ranging from about 2,000 years all the way down to 30,000 years. And so we're trying to really pinpoint exactly where each of those different stratigraphic layers is.
We tore off all the top of this, which is all recent stuff, and then there's this red layer, and you can see this red layer right here, which is Holocene, recent passage. It's old, but not as old as we want. And then we're in this gray layer, which is the youngest layer that we care about. Okay, 0 is everything above. And so we're carefully trying to not go to the next layer, which you can already start seeing, which is this sort of rocky next layer.
So there's a whole process to collecting the microfauna. Because the bones are so small, it's really difficult to just excavate in the same way that we're doing for the megafauna. So what we do instead is we take out really large sacks of sediment. It's dirt and rocks and bones all mixed together.
And we're taking off one layer at a time and putting it in bags, and then Dr. McGuire is going to take it back to Georgia Tech and sift through all these and look for all the microfossils that she told you about. We'll take it off one layer at a time, clean it off, then go to the next layer, and then do that for 4 layers.
If this fossil site were not 80 feet below ground, then I would be able to pull out so much more sediment, and I would be able to have a lot more microfauna in order to do my analyses. And I'm having to be very efficient because we're a little bit limited in, having to ask our friends to pull all of this dirt up these ropes every day, right?
If you have all this dirt, you can't see anything, so we put it in screens, and then we wash away the dirt, and it leaves us with the small fossils that we can then identify. We're doing the quick and dirty screen washing on site, so we don't have to bring 60-pound bags of dirt home. We only have to bring 10 pounds of little rocks and pebbles to sift through in the laboratory. So one large, like 40 or 60 pounds worth of sediment is reduced to basically this. So that's not too bad. People who are interested in paleontology, who want to help, this is the perfect thing for them. You poke through, and anything you think might be a fossil, you set it aside, and that way she'll only have maybe a cup full of things to look at rather than thousands and thousands and thousands of specimens. So in paleontology, we love our volunteers.
As we're picking through the microfossils, the biological gold are the teeth. So we can really identify species very easily from their teeth. And especially if we find a mandible or a maxilla, which is an upper or lower jaw, if it has teeth in it, we'll always put that in a little vial so that in case the teeth fall out of it, we'll know that that's associated material.
For me, I get most excited if I can find teeth, because my research depends upon large mammal teeth. So any teeth we find that I decide I want to sample somehow make their way to the laboratory in Rochester, where I clean it up and pull out my dental drill, and I drill the samples and put them in the mass spectrometer so that we can not only figure out what the animal was eating, but also what time of year it was eating that. And we can also look at how much it rained and at what time, and get a general sense of temperature variations, which is really cool stuff to be able to understand what was going on in past climate.
One of the ways that we do paleoecology effectively is that we try to bring in multiple lines of evidence. And the isotopic record gives us a sense of the environment that isn't showing up in the pollen record. Pollen is the most common fossil on the terrestrial landscape. It's produced every year in massive quantities. Other things can decay, leaves can get broken, but pollen, it's at the micron scale. We go to the sediment wall and you clean the face off, and then every centimeter you take a little bit of material and put it into a bag. We ended up with over 500 samples. From this centimeter thick unit of dirt, we functionally digest it. Pollen is like a natural plastic, and so it's really resistant to chemicals. And so we can dissolve the rock and we can dissolve other organic material, and the pollen grains will remain. By looking at each sample through this sequence of dirt, we are able to look at changes in the relative abundance of different pollen types. And we use that to infer what the environment was doing.
So all the fossils that we are excavating in our time here are all being deposited in the collections at the University of Wyoming Geological Museum.
So here we have just a small subsampling of bones from the Natural Trap Cave. I use the information that she's provided and we enter it into our database. And this is a large-scale database that includes all the information that we could ever want to know about these specimens. And then we have to figure out how to curate them in a way that will preserve the bones for eternity. Right now what we're trying to do is essentially play Tetris. For example, in this tray over here we have bird bones with horse bones, with American cheetah bones, and bunny bones, or lagomorphs. And so these are not going to stay here. It's just a holding pattern while we figure out where they're going to go. And we're trying to ensure that the different types of animals are organized with like taxon. And we're also trying to organize them by the different stratigraphic locality in which they were found. Digitizing and imaging them is a very important step in fossil curation, and that's because only a few hundred people get to enter this room and physically look at the bones. And so we have to get the information out somehow, and so our database we have available via the web, and we're ultimately going to have pictures of every bone, and we're going to have 3D models of some of the bones available for folks to download. And so for really large bones, we'll just use a regular high-end digital camera, but we also have a scanner, and they will basically take a 3D model of the bone and make it so that you can look at it and 3D print it, just like this one that I'm holding here. Specimens that are smaller, we have a digitizing station, and that's where we take really detailed pictures under high magnification. That enables researchers to see features that you wouldn't normally get to see, as well as give a really accurate picture of each specimen. I'm really excited to have this collection because this is going to be one of the first Wyoming fossil sites that will stay in Wyoming. Curating the Natural Trap Cave specimens here makes our collection that much more important. And so it's a really good benefit for us because it will bring more researchers to the state of Wyoming and the University of Wyoming.
It's really fun because we're operating in a world that had ice sheets over it, and horses and camels and dire wolves and mammoths and mastodons and no people. And you're just thinking about, you know, the world that you know, but it's so foreign. And we're transiting it through these data sets.
Rarely do you get a site that has such a natural accumulation of specimens. It's a very unbiased record, so what we see here is what actually lived on the surface in a really kind of true snapshot. So that alone makes this collection a really unique collection because it gives us a really reliable indicator at what lived in Wyoming 10, 20, 30,000 years ago.
How does this relate to what's happening today? In Africa, for example, we have the imminent extinction of rhinoceroses, and we have elephants that are very endangered. And so what do we expect to see in that type of community? And there is some evidence that in North America, as you have mammoths going extinct, then what you end up seeing is a real expansion of forest systems because they're no longer being controlled by the megafauna that are on the landscape.
You know, Wyoming has experienced long periods of drought. We have studies that suggest droughts lasting hundreds, if not thousands of years. One thing we would want to know at the resource management level is how do our natural systems respond to a deficit in water that is 500 years, 1,000 years. Right? Because these things happen, we can expect them to happen again. And that's important for our ranching industry, our communities. Everything depends on water. And one of the things we want to do is we could use this paleoenvironmental information out of these obscure pollen grains and fossils. And so we're really pushing the data to answer societally relevant questions.
The cave has already begun to produce a clearer picture of the past. As Julie and her team publish the results of their research, the scientific community will have an opportunity to further update the Paleolithic record. The sealed cave will continue to preserve its treasures as new research techniques and technologies are developed to recover even more data, advancing our understanding of the world we inhabit. All thanks to this unassuming pit in Wyoming's landscape known as Natural Trap Cave.
Production funding for Main Street, Wyoming is provided in part by the Wheeler Family Foundation of Casper and by the members of Wyoming PBS. Thank you.